bits require some evaluations from your professor's end, it's best you inform them beforehand. Also, if my voice is lagging or something, just speak up and I'll stop and go back. Lastly, some students asked us about the procedure for registration. You do not have to inform bits about a thesis. When time comes, you will be sent an email for a PS to TS transfer, which happens sometime in September and March. It does happen twice a year, so that's not a worry, I suppose, I hope. And for this transfer, you will require an approval from your head of department, whichever discipline you're applying in. And yeah, that should suffice. And for his approval, his or her approval, you usually require an offer letter from the department you have chosen to work with. The second step is usually a pre-registration, which is slightly more complicated, but not really a problem either. You will get emails from AugSD and AGSRD from time to time, and all you need to do by then is make sure you have an offer letter and you have selected a co-supervisor for an off-campus thesis. Yes, an on-campus co-supervisor, of course. Any other queries we can take up after the presentation is done, but I hope this gives some perspective. Right. Before I go on, I should mention that neither me nor Aditya actually are a dual degree student. Both of us took up engineering and did minors in physics and then moved on to physics. So dual degree related questions we can give our best opinions on, or the best we know of, but it won't be a fact coming from us. Right. So my project, my interest was in atoms and molecules in general, and I had taken up my PS1 in the field of computational chemistry, which led me to take up my thesis in theoretical chemistry. And I'll briefly go through each of these terms on the screen right now. Hermann Weyl, by the way, is a rather popular mathematician, but we don't cover most of his works in our courses. He has a great book on symmetry as well. You could check that out sometime. What he was trying to say here is that in a quantum system, as the degrees of freedom increase, the size of your Hilbert space, or in a classical analog, the size of your phase space would increase exponentially. So while the phase space increases linearly as the degrees of freedom increase, the Hilbert space increases exponentially. And hence, whole is greater than sum of its parts. Sorry, quite obvious. So this exponential scaling of bases provides both analytical and computational challenges. Analytical challenges are in coming up with a good theory to describe the increasing degrees of freedom probabilistically and accurately. And the computational challenge, of course, is handling all the numbers together. While there are a few and fairly expensive quantum methods which sort of attempt to break down Hamiltonians or deal with bits of Hilbert spaces at a time, a popular set of methods are semi-classical methods, and I want to talk about a subset of those methods today. It's a very niche field, but it's also a fairly popular field. So I'll go ahead with that. You must be familiar with the diagram on the left-hand side. The anharmonic potential shown in red. When you deal with a one-dimensional system, you can express the potential energy as the anharmonic potential for most molecules, as shown here. But when you increase the degrees of freedom and select to plot any two of them against the energy, you get a potential energy surface. Most simulations at room temperature, for instance, can be run using a classical description, wherein we work only with a ground state potential energy. But even simple processes such as photoexcitation and lots of electronic processes, which I'll address later, involve or require the description of excitations in both electrons and nuclei. And although today's quantum mechanics techniques don't cover all of them, on your right-hand side, I have shown a representation of this. So the dotted line and the colored lines are actually just two representations of the same set of potentials. And whether they interact or not is a question of it depends on the basis we choose. But that, of course, is a bit outside the scope of this talk. But it is this interaction between them that interests us and leads to non-adiabaticity. And yeah, let's move on. The technique I've been working with so far is known as spin mapping. This was developed by a PhD student, Johan Runeson, during his tenure at ETH. He's still working here on further advanced methods which build on spin mapping. But let's start with something simple. We'll take a Hamiltonian of perhaps a simple two-state system. And by using linear decomposition of this Hamiltonian, we use the identity and the three Pauli matrices to split one matrix into four matrices. The next step is slightly more complicated. What we are trying to do is sort of think of it as a classical shell around your quantum Hilbert space. This shell, known formally as a representation, is a classical analog of the quantum Hilbert space. What we are doing here is moving from a set of perhaps discrete eigenstates to a set of continuous classical variables. There's a small mistake in equation 2 over here, because this, if most of you might recognize this as a block vector. So U here actually must have spin up and spin down vectors, but I omitted those. So in this two-state system, what we have first done is move from the eigenstates, which describe the Hamiltonian, to theta and phi, which are continuous coordinates on a sphere, to describe the same thing. While I've not explicitly written down the maths here, it will become a bit more apparent in the coming slides. Moving from a two-state to an n-state system, a similar decomposition is first done. And the theta and phi, which were presented earlier, can be further transformed into position and momenta of an arbitrary trajectory on moving on the potential unity surface. While this is a bit hard to grasp without enough visual stimulus, you can think of all x's and p's as a set of trajectories sampled from a Gaussian distribution. This Gaussian distribution allows us to determine a set of theta and phi for each x and p, which in turn allow us to determine the spin matrices and thereby determine the Hamiltonian. And once we have a Hamiltonian, we can go ahead and simulate the dynamics of the system. These two papers here are quite well explained in this process. 2019 and 2020 papers, the ones I'm referring to, of course. But of course, you can chat with me as well if you like. Anyways, having introduced this fairly complicated process, I want to focus on the two tasks I had taken up in my thesis, or rather in January. The first task was what's the accuracy of this method? And the second task was, can we improve this method? One small thing I would like to point out is that as we decompose this Hamiltonian, you may have noticed that the identity is written separately out of the sum. And that is because depending on the representation we choose, depending on the shell which we build around the Hilbert space, there is a scaling factor which appears outside the summation. And that scaling factor is uniform for all spin matrices. I think that can be your takeaway from this slide before we move on. But that is an essential assumption that we are making of a simply connected symmetry for all spin matrices, which we can sort of investigate more later. Ignore the last equation. Anyways, moving on. The paper in 2020 tested this method on a smaller system of the FMO complex. For those of you might not be well versed in biology, for instance, the FMO complex is a simple or is a charge transferring conjugated molecule which connects the sort of antenna in the photosynthesis process to the reaction center, allowing the transfer of photon energy from along the leaf. So for this 7-site molecule, or 7 sites being the 7 conjugated loops that you see here, the method worked quite well, but we wanted to extend that to a much larger system, and hence we took up polymers. Here, I've been studying the photoexcitation of polymers for the past 4 months. Of course, I've listed down a few applications here, but I'm sure you must be aware of many more applications of polymers. But the 4 listed here are the ones important to my work because they involve an initial photoexcitation of the polymer. The polymer we had chosen to work with was polyparaphenylene vinylene. To put it simply, it is a polymer with 2 conjugated sites. The first one is the phenyl group, and the second one is the vinyl group. Here, I would like to mention that polymers have certain characteristics. First is their long length, and second is the large degree of delocalization they allow for the electrons. These 2 characteristics allow us to study polymers as one-dimensional solid-state systems, of course with some disorder, but one-dimensional solid-state systems. I think it might help to move to a more minimalistic representation here. If you consider the slanted red block as the phenylene group and the slanted blue block as the vinylene group, a photoexcitation first leads to a localized excitation, which, depending on the energy supplied, may either remain localized or spread over a set of sites. Unless I mention otherwise, I will most likely be dealing in a site basis. For those of you not familiar with quantum mechanics, I'm just selecting the sites as the phenyl and vinyl components as the basis for my vector space. Here we see that the 2 characteristic localizations can be labeled as Frenkel and charge transfer exciton. Simply put, an exciton is an electron that did not have enough energy to become a free electron and somehow is bound to the conjugate hole that is generated by it. And like the degree of pairing it has determines how far it can localize. Moving from a minimalistic view to a more schematic view, like an excitation can simply be shown as the electron moving to a higher orbital at any given site phi. The Frenkel exciton, however, remains on the same site phi, whereas the charge transfer exciton allows the excitation to another site. This is not quite. This slide is not quite crucial to the presentation, but for any viewers interested, this transfer can take place via either a dipole-dipole interaction through the bond or through a de-excitation-excitation process through space. What happens here is that it forms a pseudo charge transfer state, which might be a bit hard to grasp, but the second one is a bit more visually easy to understand. First, we have de-excitation, a photon is released, and there is excitation on the other end. And we get two charge transport excitons on the right-hand side in both of these figures. Sorry, two Frankel excitons. But yeah, as I said, it's not too crucial to my project. However, since we are working with charge transfer and Frankel excitons together at each and every electronic excitations, it's quite hard to form a Hamiltonian only for the Frankel bit or only for the charge transfer bit. So here I've presented an ansatz where ignoring the dagger operators A and A, ignoring the operators A and A dagger, you can focus on epsilon n and jn that you should have been inside the summation. But epsilon n describes the energy of a molecule at every site of the chain, whereas J describes the coupling between different sites. So J will tell you how likely an electron is to transfer to another site of the chain at each time step. Yeah. But this, however, does not complete our model. We are still building towards a larger and more realistic model. However, since this is a simple Hamiltonian, we are considering only nearest neighbor coupling. So it's a tridiagonal matrix which can easily be diagonalized. Diagonalizing this matrix gives us a spectrum of our system. This spectrum provides us three characteristic eigenstates. The lowest energy eigenstate, also known as the leg state, is a state which has no nodes. That is, the population of the exciton never goes to zero throughout a peak. What is special about these leg states is that at a low energy excitation by a photon, these are the states which are formed. And these are known as the absorptive chromophores together. So the set of them is known as the absorptive chromophores. The other two states are slightly more spread out over the absorptive chromophores as the energy of the excitation increases. In my work so far, I have tried to model the dynamics of the leg state and the last quasi-extended exciton states, the lowest and the highest states. That's a lot of talk, and so we are moving on to the last bit of math here, which is coupling the excitons to the polymer chain. So what you have omitted so far is that the electrons on each site will actually interact with the benzene molecule or with the vanillin carbon atoms in a significant manner, which is the crux of non-adiabatic dynamics. That is, the electronic subsystem cannot be separated from the nuclear subsystem. And to this end, in our simplified model, or rather a realistic simplified model, we introduce two more terms. The first one is the coupling between an harmonic oscillator, which mimics the vibronic or like the vibrational normal modes of the molecules, and the energy of the vibrational normal mode itself. So A here is the linear coupling term. So once we have a model ready, we move on to measure something. What we are measuring is the population of each site at time t, and we are initializing in an eigenstate A at time 0. If you're unfamiliar with the notation, just focus on the fact that we are moving from an operator A to an operator B, or like our observations are from an operator A to an operator B. Since we are starting in an eigenstate, operator A is a bit more complicated to write down, and it's not important to this presentation. It's not important for this presentation, the complete form of this operator. But what I would like to point out is that here again, skipping a few steps in the middle, we have converted our operator from bracket notation to continuous variables x and p. So yeah, finally, if we come to the dynamics bit, where I initialize the system in a leg state, or the lowest eigenstate, and we observe that it forms peaks from time to time. And these peaks dissipate over a certain time. While this is not the most interesting system, I admit, what we see during these peaks is known in literature as a vibrationally relaxed state. That is, the coupling to the vibrational modes or the Holstein bit of the Frankel-Holstein Hamiltonian allows a stronger localization of exciton population. But I think we could move to a more interesting dynamics, which is the higher energy eigenstate. Here we observe that since we began in an eigenstate which was spread over many chromophores, the eigenstate, regardless of how it starts, ends up in the chromophores or is tending towards the chromophores in the end. It might be if you remember a few slides ago, I showed a figure with 3 peaks. Those are the 3 peaks which appear again at time 100 femtoseconds. 100 femtoseconds is actually a short-term limit, because at longer times the system will lose its energy to environmental Bach modes, and not only to the nuclei, and it will equilibrate all again. So, yeah. So this simulation was what I had submitted as a part of my thesis work. And while you might, I'm sure you might agree this is a short project, but the duration of 4 months is usually not sufficient to lead to something significant in the theoretical field. So while this was one of the queries which had come to us, if publications are necessary during a thesis or before a thesis, it is not, it definitely helps, but it's not a requirement, especially not if you're working in a theoretical field where it is, where computational or experimental progresses don't really make a difference, or are not as important. Lastly, I would like to focus, show you the other project I had been, or rather have been working on. Before that, so far we have only looked at the population dynamics, but there are many more observables in the physics of polymers which I can take a look at. For example, here I have just shown the displacement of the nuclei due to the exciton. So the y-axis n shows the marks a nuclei n sites away from the exciton. So if the exciton is on the nuclei, there are periodic displacement maximums which appear, whereas even at slight distances away from the exciton, there is no effect on the structure of the polymer. So another conclusion you can draw from here is that the increased disorder introduced by the exciton is the one that leads to the vibrational relaxation. This can be proved rigorously mathematically, but of course it has been omitted here. Another thing I have been taking a look at is many variants of spin mapping, which I didn't have the opportunity to introduce today. Lastly, if you remember, I had presented in a very early slide that all spin matrices were being scaled equally in the generalized spin mapping approach. However, the symmetry which is assumed by generalized spin mapping does not apply to all molecules everywhere, and it especially does not apply to the Hamiltonian I had picked, which was a tridiagonal matrix. So given the fact that all the off-diagonal terms except the first off-diagonal are 0, we try to simplify our spin mapping approach and introduce weights to every spin matrix. This will be more apparent in this slide, because as I introduce weights hi to the matrices, the scalings are divided into different sets. And one of the interesting observations I've made so far is that the weights divide the spin matrices into different spin orbitals of electrons. So the first set is, of course, the identity. The second set is the p orbitals. The third set is the d orbitals. The fourth set would be the f orbitals, and so on. Again, this might require a few more mathematical equations here to explain. But at the moment, I'm trying to implement this alternative mapping approach to a 3-site FMO system instead of a 7-site FMO system that I had shown earlier. So we can actually take a step back now and maybe look at what I've covered so far. First, we took a look at spin mapping and a brief overview of it, what excitons are. We built up to a model of Frankel excitons. We took a look at a few slides showing the dynamics of a lower energy eigenstate and a higher energy eigenstate. And we looked at a possible theory of a reduced mapping approach. So that's actually all I have so far to present, and hopefully in a month more, I'll know if my reduced mapping works. Lastly, I'd like to thank, of course, the mentors, Dr. Richardson, who offered the opportunity, and the postdoc and PhD student who have been mentoring me. And yeah, that's theoretical molecular dynamics. I believe I'm done. So if you have any questions, we could take short questions now, or I'll stop sharing. Yeah, Manas, I think I'll take your question later. We'll move on to Aditya's presentation then.
Hi, can you hear me? I'm Aditya Pujari. So hi, my name is Aditya Pujari, and wait, I have to start sharing. Okay. I hope my screen is visible. So hi, I'm Aditya Pujari. I'm a friend of Aamod's. As Aamod pointed out, we're not from physics, we're from chemical engineering. Both of us have done a physics minor out of interest, and we ended up in physics now. So like I think one of you asked, do you have to do a physics minor to do a thesis in physics? तो नहीं ऐसा कुछ नहीं है. It's just that whatever topic you do, it has to be related to your discipline. So like Aamod's thing was about molecular dynamics, which is pretty closely related to some aspects in chemical engineering. My thing is fluid dynamics, which is again essential in chemical engineering. So that's why you were sort of able to do some things that were more interdisciplinary in nature. So like in case you're a dualite, and if you want to do two theses, then each of the thesis you do, it has to be related to that particular discipline. So if you're maths plus CS, one of it has to be related to maths, one of it has to be related to CS. Or you could do just one whole 1 year long thesis, and that could be related to both of your dual disciplines. So yeah, having said that, I'll continue with the talk. Oh yeah, first of all, how I landed with this thesis. So basically, I knew that I was interested in fluid dynamics. Like I like the physics and the maths part of it, and like fluid dynamics happens to be one of those areas in chemical engineering is areas in chemical engineering that's a lot more physics-ish. So so that's why I chose to go with fluid dynamics. So I was trying first abroad, if we can get, if I was able to try my luck there. But I actually did get in to one place, University of North Carolina, under a professor in applied math. Again, the department of the professor you will be working under does not have to be chemical engineering, like in my case, but like the topic you will be working in has to be associated with your core discipline. So I was able to get a thesis there, but it wasn't funded. So one thing you might want to note down is that it's hard to get a funded thesis in the US. Um, However, it's much more easier to, wait, maybe not much more, but it's more easier to get a funded thesis in Europe, um, as Aamod's was. So, so those were two places where I tried. I couldn't really find anyone with the same interest in Europe, or maybe I didn't look hard enough. Um, So I kept places in India as a backup. So some of the places I had applied to was, like, first of all, ICTS, International Center for Theoretical Sciences. Those of you who haven't heard of it, it's basically it's one of the many centers of TIFR. So TIFR ka main center is in Mumbai. Then there's this in Bangalore. There's also National Center for Biological Sciences in Bangalore. It's right down the road. And yeah, so you can try places like TIFR. You can try places like IITs. You can try places like there's this one place in Bangalore called JNCASR, Jawaharlal Nehru Center of Advanced Scientific Research. Uh, so those were some places I tried. So like I just like to say that like you can keep backups, you can mail multiple guys, you can say a tentative yes to multiple profs and then see how things finalize. So on to the topic. So much ado about point forces. So I worked with Professor Ramya Govindarajan at ICTS. Um, I've actually early graduated, so I did my thesis in 4.1 and my 4.2 was like empty. So that's how I chose this to be because like Professor Rama, she was only accepting students for a duration of 1 year. Um, and so I took that as an opportunity and finished up all my courses in 3.2. So like if you get 1 year opportunities, you can definitely try for it. Try for finishing off your courses. I'd say, like first of all, you will be saving 1 semester ka fee, and you'll also get more exposure, which you might not get if you stay back. So onwards. So yeah, the more formal title is Point Forces in the Context of Biogenic Ocean Mixing. So the outline of my talk, basically I'll first be talking about biomixing of oceans, what that is about, and what it has to do about animals. Then how can we model these animals and how they interact in a fluid using point forces in a fluid. So the basic idea is that you know how like we've learned in electrostatics that like you can have point charges placed in different places in space, and like you can just add their electric field, superpose them. So you can do the same funda in fluids, given that you're in some certain flow regime. So I'll briefly talk about that. Thereafter, before we moved on to modeling animals using point forces, we first looked at a few simple problem statements. So one was about falling spheres. Um, the other was about racing micro swimmers, which I'm still working on currently. And last but not least, this one is still incomplete. Okay, yeah, it is the least. Staring at shrimp and writing equations to model the shrimp. So I'll come to why shrimp in particular. I've made those two boxes of biomixing and falling spheres green because I think I'll talk more at length on those two topics. Yeah. So ocean mixing is highly underrated. Like we all talk about climate change, we all talk about how we're messing up the climate and stuff like that. But like sometimes we forget that the climate and the ocean is very interrelated. And we only know the climate of a region as good as we know the ocean structure, ocean circulation in that region. So like there was this one really nice quote by an eminent oceanographer, Carl Wunsch and Walter Monk. So they said that without deep ocean mixing, the ocean would turn within a few thousand years into a stagnant pool of cold, salty water. और फिर मच्छर काटेंगे. Yeah, so overturning circulation. So like in the ocean, there's this constant circulation that goes on, and the time scale of this circulation is like hundreds of years. It's slow, but it's going on. So like this picture here, it shows like a rough map of which circulation goes where and stuff like that. And this circulation is important in the sense that the water that is on the top, surface, what do you call it? Surface currents. Surface currents tend to sequester carbon dioxide, and once those surface currents go down into the deep parts of the ocean, the sequestered carbon dioxide is sort of trapped in those deeper currents, and that really helps in sequestering carbon dioxide. And it's very crucial to understand this. And the fact that it's 2021 and we still don't understand this and global warming is upon us really highlights the fact that we should be studying stuff like this. So the eminent oceanographer I just mentioned, what he was doing was he was trying to quantify ki ye circulation ka budget kya hai, how much energy does it really require. And so this was early 2000s, and they realized that somewhere there's a lacking of energy. Like they accounted for winds, they accounted for tides, and even after doing so, like those are the two main things of energy sources, winds and tides. Even after doing so, they realized that there's some energy deficit in the circulation. So this sort of sparked a question ki ye baki energy kahan se aa raha hai? So that's where the thing about biogenic ocean mixing comes into play. Yeah, so people started to explore the possibility that maybe creatures swimming around in the ocean might be contributing to the energy that is required for this oceanic overturning circulation. So this started a 20-year-long academic debate. It's still going on, investigating whether biomixing is real or not, whether it actually contributes or not. So like the current consensus as of 2020 is that it doesn't contribute. But it is known to be significant at local scales. So what I've been doing in this project is to maybe provide theoretical evidence to show that biomixing is actually happening at local scales. So that's one thing. Another thing about animals, and especially when we talk about animals in the ocean, over like around 90% of the biomass in the ocean is concentrated in tiny critters like plankton, zooplankton, phytoplankton, shrimp. And if we're able to understand how these tiny things move, then we might be able to understand how they contribute to nutrient transport in the environment. And another important thing is that these tiny things, they actually produce a lot of oxygen. In fact, I think one study I read said that they produce more oxygen or actually sequester more carbon dioxide than trees do. So it's really important that we study these things. To start modeling these tiny things, you could look at the top right figure I have here. So the left one kind of looks like a sperm, and the right one, it looks like, I don't know what it looks like. So if you want to model it using a point force, you can see here that the sperm can be modeled as like 2 point forces pointing in opposite directions, whereas the other one can be modeled as 2 point forces pointing in the same direction. So that's what we're trying to do essentially, stare at a shrimp and find the right combination of point forces to create the flow field it generates. And then like once we have the model ready for one shrimp, what we can do is take an aggregation of shrimp and try to model that. And try to mimic experiments people have actually done with migrating shrimp in tanks. So like these two images here, this is a tank in which this is actually a schematic of the experiment group from Caltech did. And this the graph shows the result. Basically, they started with like a step function of salinity, and they over multiple migrations of shrimp, they showed that the salinity it sort of tends to diffuse over the water column. So okay, so now we want to model active particle swimmers with point forces. So we need to have a theoretical background about point forces. So let me talk about point forces. I won't go too much into the math. So you must have heard of the Navier-Stokes equations. So like, I get a pointer here. Yeah. So this is the Navier-Stokes equation. Uh, each of these terms means something. This is the pressure term. This term represents the force. Okay, so the Navier-Stokes is basically a force balance over the fluid. So this term represents the force that comes from pressure. This term represents the force that comes from this viscosity. And the left one is the force that comes from acceleration. Um, and apart from the momentum balance, you also have the mass balance, which is the continuity equation. So the Navier-Stokes is incredibly hard to solve. No one has solved it analytically yet. But the fun thing is that if you focus on low Reynolds number flows like laminar flows, um, you can actually get analytical solutions. So if I go ahead and say that my Reynolds number is really small, meaning that I'm in laminar flow, so Reynolds number मतलब inertial by viscous forces होता है. तो अगर Reynolds number small है तो your inertial forces are small. So if my inertial forces are small, I can neglect this acceleration term. And what I'm left with are these two terms, the pressure and viscous. And because I want to be modeling a point force, I place a point force F at some position in the fluid. So that is denoted by a delta function, like just how you do it in electrostatics, a charge represented by a delta function. So that's how you represent a point force. So it's called a Stokeslet. I'll try not to use jargon here. If I have a point force dipole, it's represented by this, and it's called a Stresslet. And let's say I don't want to model a flow that's zero Reynolds number, because that's a really unreal case. But say I want to model a flow that's a Reynolds number of order 1. Then what I can do cleverly is that I forgot to mention one thing, that we're talking about steady state. So this term here is being completely neglected. We're just talking about steady Navier-Stokes. So in the case of wait 1 second. Am I still on?
No, your presentation's gone.
Okay, 1 second. That's funny, that never happens. Can you see it again?
Yeah.
Okay, cool. So where was I? Yeah. So if I don't want to model a low Reynolds number flow where Reynolds number is 0, and instead I want to model a Reynolds number flow of order 1, say, what I can do is, one second. Yeah. यहाँ पे जो term है, what I can cleverly do is the u sitting outside, the velocity sitting outside, I can take that to be constant and equal to the mean flow in my problem statement. So that's what we've done here. The capital U is taken to be a constant, and baki this the mu जिसका derivative ले रहे हैं, that remains our usual v which we calculate the variable. So this is a very hand wavy way to tell you, but like there's a rigorous way you can show that to some extent this approximation is pretty good. And similarly, this was for a point force. If you want a dipole, force dipole, you can rewrite it in this manner. So yeah, so the nice fun thing about this is that all these equations here you see, except Navier-Stokes, are analytically solvable, and they're also superposable. So when you say superposable, that means basically these equations are linear. So you can see that all the equations are linear in V and also P. So because these point forces are superposable, I can just put point forces at different parts in the fluid and just add the resultant velocity solutions and get the resultant net flow. So this is sort of how it looks like. So this is one point force pointing downwards. The contours represent the velocity magnitude, and the gray tiny arrows, they represent the direction of the fluid. So if I add another point force pointing in some other direction, that's how the flow would change. And like you can really play around with these and make different shapes with the streamlines. So like my prof had COVID beach mein, so I sent her a get well soon card. So like I made these streamlines from those point forces. So yeah, you can do plenty of stuff with point forces. It's like Lego blocks. You could just put them in any manner and create stuff with it. And the best part about these lines is that all of them are analytical. It's nothing numerical. All have equations. Okay, so carrying on. Yeah, so now we have a background with what the point forces are exactly. So now we can move on to more solving that problem statement I was talking about earlier. So the problem statement is as follows. Let's say you have an array of spheres and they're kept in a fluid and they're falling. So each of these spheres are spaced d distance apart, and each are the same size with radius a. So now we want to see what the resultant dynamics would be. So you can, I'll approach this more intuitively. I want to avoid the math. Say that these spheres are perfectly in their positions in a perfect world. And if I let them go at t equal to 0, all of them will fall nicely in a vertical fashion. However, the interesting question actually in this problem is that if I give some of these spheres a perturbation, how would that perturbation grow with time? So that's sort of the question. So I'm going to go ahead and just give you a spoiler. And 1 second. Yeah, so you know how you'll find this in many physical systems, that a physical system can be characterized by normal modes. So like you must have learned in one of our physics courses where we have a double pendulum, and the double pendulum, when you solve the equations, you find out that you have two normal modes in it. So one of the normal modes is where, I hope my screen is visible. Sorry, my video is visible. In one of them, the pendulums, they swing together, and in the other one, they swing in an opposing fashion. So those are the two normal modes. And no matter which initial position you start with in the pendulums, you can always write their motion as a superposition of those two normal modes. Uh, so that's the similar funda applies here as well. I'm going to show you two normal modes of this system and what it does. So on the left is the most unstable mode. So all of the particles have been perturbed in a particular fashion as so as to make this mode the unstable mode. And if I hit play here, you'll see that all the particles, they gradually clump together like that. So that's the unstable mode, all of them clumping together. And the stable mode is all of them are initially perturbed in a certain fashion, and as they fall in a parallel fashion. So they sort of stabilize each other. Each of the perturbations hydrodynamically, it neutralizes somehow, and they don't clump together. So these are two stable and unstable modes, and any initial perturbation of this problem can be written as a superposition of these two stable and unstable modes. So on the top, I've written like the eigenvalues of these stable modes. So a stable mode is essentially an eigenvector of your physical system, and the growth rate, so how fast these modes converge or stay parallel, that is captured with the eigenvalue. So the eigenvalue here is beta. And alpha is a constant of the system. It is a characteristic of the radius of the, the distance between the spheres and the viscosity of the fluid. So this was the spoiler. This is actually the result I'm supposed to be getting. So this is how I got there. So first of all, I have to show that modeling a sphere with a point force is just fine. So I did some preliminary calculations and made sure that the error is okay. And it turns out that the error is like just 2.75% from the real experimental value. So we're doing all right here. By the way, this thing, so this is the velocity solution of the point force. Just to show you how it looks like. So these are the falling spheres. The velocity at the kth position is essentially adding all the velocities induced by each of these k plus lth guys at this position. So that's essentially what this equation says here. And I do it for all the infinite guys here, except for the guy itself. So L isn't equal to 0. So this is the very nice case where all of them are just falling without any perturbations. Whereas ye niche wala, so this is the resultant solution you get, and you can see there's only a minus j vector. So there's no vector component in the x direction. So you can see all of them are just falling vertically downwards. Now, if I introduce the perturbations and carry out the same exercise, this addition superposition equation essentially remains the same. And if I put in the velocities and do some algebra, which I will skip, we end up with these two expressions for the evolution, the rate of evolution of the perturbations. So I think I forgot to mention here that eta and xi are the perturbations in the y and the x direction respectively. So वो दो कैसे evolve करते हैं with respect to time, that is what I get with these two equations. So let's go ahead and say that I'm just going to include the interactions with the nearest neighbors because the ones that are far away, they won't really interact much. So if I put L equal to 1 and -1 in both these two, I get these two simple, cute-looking equations. And if I rewrite these equations in matrix form, that would look like this, where x is essentially, you can sort of say your phase space vector or something like that. And then as goes the usual technique to solve a differential equation, you put a trial solution. And a trial solution with, so x naught is your initial condition, and a trial solution also has an undetermined constant. So that's beta right here, sitting up in the power. And e raised to jk and d, that is your sine cosine thing, written in complex format. So on solving that, you get the beta, and accordingly you can get stable and unstable modes. And essentially, if I code these equations back in and verify with the video I showed earlier, I get what I saw in the video, in the simulation. So yeah, so the beta, when you put it back, you get these specific expressions for eta and xi. And if you can, if you put in, if you actually calculate which direction these guys are pointing for each of the spheres, you'll see that this guy is tending upwards. This guy is tending this way. So these two are both tending away from their mean position here. And that means this mode is unstable. So that would mean beta equal to 2 alpha corresponds to the unstable mode. And likewise for the most stable mode, where this guy is tending back to its mean position from the perturbation, and so is this guy. So this we were successfully able to reproduce. This is actually a really old paper, 1970s ka paper, where this guy whose research was funded by the Xerox Corporation, I don't know why, he did this experiment and he showed that. So we reproduced that. Uske baad mein, so this was a really nice first exercise for beginning to model things like swimmers. So the thing about a swimmer is that, like, where a swimmer is an active particle. So the difference between an active particle and a passive particle is that an active particle it conserves momentum. So like if I'm a shrimp in the ocean, then there's no external force on me. Like assume I'm neutrally buoyant. There's no external force on me, जिसके वजह से I am moving due to internal forces in my body. So if you do a force balance on my body, there will be a net zero force, or if you time average it. So in that sense, instead of using a point force to model something like an active swimmer, I would want to use a combination of forces, जिसका net force is zero. So that's essentially what I'm doing in the next problem. So the next problem is exactly the first problem, except instead of falling spheres, imagine micro swimmers at the starting line of an Olympic race, and each of them are spaced d distance apart. And at t equal to 0, they start swimming at a constant velocity u naught. And uske baad mein I need to see ki are they going to collide into each other? Is an initial perturbation going to exponentially increase, and things like that. So this is just one of the problem statements we were pursuing, but this one isn't complete yet. So I'll go on to talking about the shrimp. So this is the theoretical stuff I've been doing. Along with the theoretical stuff, the theoretical stuff is basically going to be used to reinforce the experiment and explain the experiment. So that was one thread of work. The other thread of work is the experimental thing. So yahan pe, I'll just go ahead and show you a video. So in this video, you have, Where's the play button? Yeah. You have a shrimp, a baby brine shrimp. So this thing is really tiny, as you can see. So this thing is, this length is 1 centimeter, and that's the tiny shrimp there is. So this is the scale of a majority of the swimmers in the ocean, and it's hard to imagine that tiny stuff like this swimming in our aggregations of thousands can actually cause nutrient transport in a body as big as the ocean. But apparently that's what happens. So that's something we would really like to explain, um, especially if we want to understand the ramifications of climate change and what impact they could have. If climate change could have an impact on the breeding grounds of these things, then it could really mess up how much carbon gets sequestered because of them. So with that, I'll end with another video. So so the one you saw here was the shrimp swimming in a droplet. So after that, what I did was I sandwiched the shrimp in a 2 or 3 mm water layer between a glass slide and a cover slip. And then I tried to, so basically what that does is it restricts the movement of the shrimp in one plane. So once it's restricted in one plane, it's easier to focus on the shrimp, and also the fluid dynamics are a little bit easier. So I'll show you this. So that's the tiny shrimp. I think there are 2 shrimp in there. And I apologize for the very dirty glass slide I'm using. This was just a trial experiment. And yeah, I bumped the table. So that's what these tiny things are. This stuff, by the way, is fed to shrimp. No, not shrimp. It's used as food for fish in fish tanks. So that's why these things are readily available. Okay, so that's about it. And do I have a thank you slide? Yes, I do. Thank you. Thank you, CTE, for this opportunity to present my work. And I also like to thank my professors, family, friends for the support through these weird times. And um, it's been a year since I've been here because I started in my first semester, 4-1 ka, and 4-2 I just continued. And because of COVID pandemic, I decided that I also needed some more time to decide on exactly what I want to do after this. So I decided to continue 1 more year in the same group. So I'll be in the same group at ICTS for another year. And yeah, let me know if you have any questions. Oh, also, yeah, as Aamod had mentioned, yeah, there are long-term. I entered ICTS through a long-term visiting student program. They have a program like that, and I think there are programs like that at different institutes, also like Raman Research Institute as well. So you can look at those options in Indian institutions. And so like it's all the accommodation and the funding is everything is covered through that. So uh, you can check that out on the ICTS website. It is there. the visiting student program. So, yeah.
There are some questions in the chat box if you could take a look at them.
Okay, sure. I'll start from the top. Hmm. Okay, so Manas Lohani, I think I answered this one. Okay, any suggestions with people like me with very low CG? Um, just go ahead and apply, man. Like even people with that sort of CG can get places, and of course, like some people might decline, but there are always opportunities out there where you can get it. And like CG is just it basically gauges how serious you were during the course. It may not reflect how interested you are in the subject, and interest in the subject is really important when you're doing a thesis or research anywhere. So just go ahead and apply. Maybe you might want to talk to other people who have a similar CG. Um, okay, so next, Karthik Suresh, when do the confirmation emails usually come out? And if the HOD approval is there, does thesis mostly get approved? Okay, so for the second question, if HOD approval, so all you need for an approval is you need the HOD ka approval, um, and you need a an on campus co-supervisor. उन दोनों का approval चाहिए, बस हो जाएगा. Um, and the first question, and do confirmation emails. So like by confirmation email, are you referring to the confirmation email you get from the other institute in which you're doing your thesis, where you want to do your thesis? If it's that, then like basically through the conversation through with your professor, you would want to let the professor know that you have to inform bits by this date or this week of this month, and they'll arrange for something like that. So like they might give you an offer letter on their letterhead, on their institute letterhead, and that will suffice. If it's like if you've gone through a program like the one I went through. So when you get accepted into the program, give you they give you basically an acceptance certificate. So you can show that. Mm. Okay, Nishit, I think you asked it twice. Okay, you're a dualite, just finished 3-2. Yeah, man, just start applying. Okay, so I guess you'd be able to go for a thesis in 4-2. Wait, you guys have 4. Yeah, this is a perfect time to start looking for thesis. Like if you want to go in 5-1, this is a really good time. You can start weighing your options, and yeah. One thing to mention is that if you have a low CG, it's always better to start earlier, sending emails, because it's sort of a first come first serve thing. Like there would be some positions, some problem statements available in a certain group, and if a high CG guy tends to mail that prof, and uske baad mein if you email them, then you might have a lesser chance. But if you can email earlier, you'll have a better advantage. So um, like I think one of my seniors, like he had like a almost a 7 CG, and he was able to get NUS, National University of Singapore. And this was before COVID, so we actually got to go there. Okay, so Neil Shaha, how does one conduct experiments on this? Like, how do you get the data for the behavior of the fluid with? Okay. Um, should I answer technical questions first, or how many questions are there? Yeah, I think I can answer this one. How does one? Okay. Right. So the idea of the experiment is to look at a shrimp and then look at the fluid flow around it. So finally, after so what I do is basically fluid may I put tiny seeder particles. So these particles, unka density is equal to that of water, and so these particles basically faithfully follow the flow, and then you can take pictures of these particles. So like at instant t1 and instant t2, I take two pictures, and between those two time steps, there will be a really small time gap, and I can just compare ki kaun sa particle kahan pe gaya with an algorithm, and based on that, because I know the time difference between the two frames, I can calculate the velocity. So this thing is called particle image velocimetry, this method. There's tons of literature on it. You can just look it up. The Wikipedia page also has a lot of stuff on it. Okay, so Apurva, when do the confirmation emails? Okay, I think I answered that. While applying for thesis, do we need to prepare a proper research proposal or just? Okay, yeah. You're not applying for a PhD. For a PhD, you need a research proposal. For this sort of stuff, like you just need to express enough interest, ki, and you want to tell them ki, why you are interested in it and why you might be fit for their group. Like maybe maybe it's a coding, maybe it's a computational group, maybe you have some coding skills, you could highlight that. You can show them that you're suitable for the job by showing them the past projects you worked on. So like when you send out the email, you should attach a CV and mention the projects you've done. And yeah, like no need to give a research proposal. You can maybe, if you've been following that prof or that group for a while and you have some idea, you could just mention a brief line or two about it. But these professors are like very busy and they don't have much time to reply. So make sure, at any cost, make sure your email can be read within 2 minutes and it's not too long. Okay, so when do the pre-registration confirmation emails come out? Aamod, can you help me out here, or anyone else?
Pre-registration confirmation comes out much later. So once you fill in your forms, you can essentially start your thesis if you have HOD approval and like all your documents are in order. So I started my thesis in January. My email came to me mid-February. And if they had declined it, then there really was no way I could have gone back to India or something. So don't worry about that.
Yeah, so I think that answers it. Yeah, same. I also started my thing in May. Like last year, after online courses ended in April, I started first week of May, and yeah, sub thesis formalities, it happened in August, I think. August, yeah, almost September. So I was already working on it. So you can start working whenever. Formalities are just formalities. Okay. How did you decide what specific topic you wanted to do your thesis in? This is a really nice FAQ. Yeah, stay hungry, stay foolish. Like, if you don't know what to work in, your best bet is to go for the thing you are even the slightest interested in. And like throughout engineering, I tried to do that. Like at first, I had some interest in molecular dynamics, what Aamod is doing. So I did one project with a prof on campus regarding that, and after a semester or two, I realized कि no, this is not really my thing. So उसके बाद I tried some other different field, and that happened to be fluid dynamics, and I happened to like it. After that, so now I'm doing my thesis. इसके बाद में when I apply for a PhD, I might go for some new different field completely. So try to take the hint from even the slightest inclination or slightest interest you may have, because that's your only best bet. Otherwise, you could go for, if you're equally inclined to any topic, you might want to go for something that is, you might want to go for a hot topic or something that has, I don't know, good opportunities later on. Maybe job opportunities after PhD or something like that, or research opportunities. Okay, Mahajan kya पूछ रहा है? To what scales does your mathematical model extrapolate to? For example, wiggly things in increasing order of scale. Yeah, this guy is my friend. बस बकचोदी कर रहा है. Okay, so sperm greater than shell greater than something big wiggle. Okay, something big wiggle might be a whale. Why am I even answering this? Okay, Aamod, you replied. Okay, Anirudh, if we're a dualite, then can we do a thesis in both semesters in one discipline? Oh wait, what we're doing, if we're dualite, can we do a thesis in both semesters in one discipline? If not, then we show a correlation to correlation. Yes, to your second question. So I know this senior. I'll say this off the record. It is recording. Okay, whatever. I know this senior. So he was in Chem-Eng and he did a physics, and he was a reverse dual to physics. So he was really interested in physics, astrophysics in particular. So he did a year-long thesis at I think the same place or two different places. I don't remember, but for the thesis that is supposed to correspond to chemical engineering, what he cleverly did was in the title he put something jiska naam something resembles something about fluid dynamics, and the HOD was fine with it. He didn't bother much. So, but if you actually went and read his thesis, it had very little to do with fluid dynamics. It was much more astro. So I won't name this fellow, but it's pretty clever what he did. But like it really depends on how critical your HOD is. Like I heard in Triple E, the HOD asked to like submit an abstract of what you will be doing and all that stuff. So like the chemical HOD was pretty chill about it. As long as you have an offer letter and as long as your title is or subject is somewhat related to your field, then you can get by. Okay, Bhanu, I'm in chemical. So should I get the approval from the chemical HOD or physics HOD, even if I? Yeah. So regardless of what your thesis topic is, the approval has to be from your own department ka HOD. Okay, Aamod replied. Sania, I must have missed a talk. What is your model analyzing the movement of a system of a large number of shrimp or interaction within the system? Okay, so what I'm doing is first I take one shrimp, I look at the flow field around it, and then I try to find the correct combination of point forces to model to get the same flow field I saw in the experiment. So once I get that, I have that combination of point forces, maybe two pointing downwards and one pointing upwards, just for example, say. And so then after that, what I want to do is, there's a huge aggregation of shrimp now. So I can now just model it using point forces. So if I have 10 shrimp randomly placed in a water column moving upwards, I can group those point forces and I can have them migrating upwards and see how the flow field around it is, and see how the nutrient transport occurs. So yes, I am sort of interested in interactions between multiple streams, but at this level, um, it's just one stream because even getting the thing for one stream is not as easy as it looks. Okay, so BPHC is not offering physics minor, so do you think it would affect my chances for thesis and higher education given I take up as many physics courses as I can? I don't think. Physics minor is like, you can always do physics courses. Um, Physics minor will just come along with those courses. So like anyways, we have 5 open electives. If you choose to do all of your 5 open electives in physics, it just comes with a minor name attached to it. If that minor name provision is not there in BPHC, I don't think it will affect your knowledge per se. But it might not, the name of minor might not show on your resume, but you can always put the courses you did, the relevant coursework you did. And which reminds me, in your CV, you can mention relevant coursework related to the prof you're applying to, so he knows that you're the right guy. I think Aamod already answered a lot of those. Okay. Did I just reiterate all the questions Aamod answered? I'm sorry. Yeah, so what's up? I'm done. Did I bore the coordinator? Did he leave or something?
No, I'm just here. I was just
Okay.
waiting for someone to ask any questions.
Okay, sure.
Yeah, thank you very much for taking your time and doing this for us. I hope
Sure. Absolutely.
you're very interested about your talks. Yeah, I guess that ends today's thesis talks. Tomorrow we'll be having the next episodes on neuroscience, and we have interesting speakers as well. So we hope you come to watch us there also. Yeah, thank you for coming here.
Thanks. If you need any, if you have any other questions, you can PM us. You guys have our phone numbers. Surud, is there a way we can give everyone our phone numbers or email ID?
Oh, yeah, I will. Okay. Yeah, if you can share them in the chat box, or we can send them. Like we can put them up anywhere as well. It's your wish. You can put them in the chat box. Like this is getting recorded, so it goes to the invites people whom we have sent invites to.
Okay, sure. There are only 20 people here, so okay, whatever.
Excuse me, can I ask a question?
Yeah, sure. Go ahead.
This question is for Aamod Bhaiya. Bhaiya, I've read a lot about ETH Zurich, and it's my dream college. I know that it's like the MIT of mainland Europe, and I've always known it has excessively high cutoffs for everything, be it the thesis thing, master's thing, or PhD. So, what was the criteria that you think you got? I mean, where did your profile shine exactly? Could you just elaborate on that?
It does have high cutoffs for master's and PhD applications and so on, even for bachelor's. But the research is quite diverse, and you can find very good research in very specific fields. For example, I looked all over for theoretical molecular dynamics, and only in ETH did I find one group who was doing the things which I really wanted. And I wrote to them about it. And as Pujari said, as Aditya said a while ago, you just need to express your interest. At that point, I don't think my profile shined as much because I only had one project from PS1 in computational chemistry, and I had taken up a couple of informals to study molecular dynamics. And I mentioned that I had a physics minor. So my profile really didn't shine. But the professor took note of me, and then we had a few interviews, and it went back and forth for a couple of months before he finally offered it. So sometimes it's a single shot process, sometimes it's just not. And Yeah, I suppose there is a factor of luck involved as well. So
I see.
I think it depends on the discipline you want to go for. That's all.
I see. Bea, and one last question. I'm sorry if it goes a little off, but Bea, as you know, that Zurich is a very costly place, and everything. So, Bea, were you paid during this thesis? Did they pay for your accommodation and stuff, or did you have to?
If you come here as a student, you will not be paid. There are scholarships for master students if you plan on applying. As you said, you most likely might. And I was in Germany, France, Switzerland, Sweden, and most of other mainland Europe. It is mandatory that you offer employees stipend. So I am paid enough to, live comfortably. But you should also note that some European countries are putting up caps on the visas they offer to kinds of employees. So if you come here if you're looking for a long-term thesis, then you can't come here as a student. You have to come here as an employee, as I did, and that will become increasingly difficult over the next couple of years. So if you maybe come for 5 months, you're a student. If you come for longer, you're an employee. So just keep that in mind if you plan to apply.
Thank you so much for the answer. Thank you, Bea. Congratulations to you.
Cool. Also, if you have any other questions, I'm putting in my number here. I actually have another meeting I am supposed to go to. Feel free to contact me, or you can drop an email. I'll get back to you. Thanks, CT and stuff. Bye-bye.
Any more questions?
I guess there are no questions. I guess we can end the session. Yeah, thank you for coming. Thank you so much, sir.
Okay, sure. Absolute pleasure. Bye-bye, guys. All the best.